All right, so hello everyone. Welcome to our third and final pre-conference panel for the NSF DARE conference on transformative opportunities for computational modeling and neurorehabilitation. It's a mouthful every time I say it, but it's hard to believe the conference is in just 10 days. And so we really appreciate you all being part of the community and conversation and dialogue beforehand. You know, we picked a few topics for these pre-conference panels, but obviously the scope of the workshop will be much broader. A few logistic items before we get started. First of all, I guess I should introduce myself. I'm Kat Steele. I'm one of the organizers here at the University of Washington. We actually have, I think, our full PI team, except for James Finley at USC today, but we have the Valero lab at USC, and then Amy will be serving as our moderator today. A few logistic items. If you haven't already on the conference Slack channel, don't forget to introduce yourself and feel free to post any papers or other things of interest to the community on there. It's been great to see some of the activities so far. Additionally, closed captioning is available by pressing the CC in the bottom of your Zoom controls. And if you have any questions or requests, don't hesitate to reach out via the chat. We will have a question period at the end of this today. So either you can put your questions into the chat and we will keep track of them, or you'll be welcome to unmute yourself and ask at the end. A recording of this will be posted via YouTube. And so you can look for that as well, or share it with others who might have missed it. All right, so with those housekeeping items, I'm going to introduce our moderator for today. Amy Orsborn is one of our organizers for the conference, and she is the Claire Booth Luce Assistant Professor of Electrical and Computer Engineering and Bioengineering here in beautiful sunny Seattle at the University of Washington. And her research focuses on brain-machine interfaces to restore, replace, and augment nervous system function. And she will be moderating today with our two panel members who she'll introduce. So with that, I will turn it over to you, Amy.
Right, great. Thank you so much for that intro, Kat. And I'm really excited to be here today because we have two really great panelists that are going to help us discuss the generally broad topic of sort of human-device interactions and how we can think about using those for rehabilitation. And so our first panelist is Helen Huang, who's the Jackson Family Distinguished Professor of Biomedical Engineering in the joint program between North Carolina State University and the University of North Carolina. And she leads the Neuromuscular Rehabilitation Engineering Lab, which studies a really inspiring range of topics at the intersection of robotics and neuromechanics. And then our other panelist is Doug Weber, who is the Akhtar and Bhutta Professor of Mechanical Engineering and also the Neuroscience Institute at Carnegie Mellon University. And he runs the Neuromechatronics Lab, which works at the intersection of neuroscience and engineering to both develop new therapies and also study sort of fundamental questions of sensory motor function. And so, like Kat mentioned, we'll start off with sort of a guided discussion. I have kind of a couple of questions to kind of get ideas rolling. If you have anything to chime in, as those discussions are going on, feel free to put them into the chat, and then we'll switch to sort of a broader Q&A. All right, so I think to start off with, why don't we kind of get a broad sense of kind of what got you interested in this, in particular, kind of intersection of modeling and computational questions and rehabilitation. And I'd also love to hear a little bit for both of you of kind of what phase in your career, right, did sort of those interests in modeling develop. Some people really start as modelers and maybe branch out. Some people go the other direction. So maybe kind of, maybe we'll start with Doug.
Oh boy. So I think my career path is interesting, certainly not linear by any stretch. As an undergrad, I started in electrical engineering because I was interested in robotics and automation. Took my first controls class as a sophomore and thought it was really interesting. Then I took an internship at an industrial automation company and found the work really boring. And so at the same time, I had met some biomedical engineering students at my university and discovered that they too were interested in controls. but rather control of movement and, you know, biological functions. And so that was sort of the first aha moment for me that, wow, you know, this math and stuff that I like so much can be applied to more interesting problems than making motors turn at the right speed. And so that was kind of the change in direction for me. And then, you know, at that point, I had no idea that I would end up going to graduate school and sort of making research a career. It was a small institution that I had went to as an undergrad, and research wasn't really a thing. But the more I studied, the more I realized that, well, that might be an interesting path to go. And so I ended up going to graduate school to do research in Jiping He's lab at Arizona State, and working in close collaboration with Andy Schwartz to study the neural control of arm movements from the standpoint of motor cortex. And so, yeah, so I sort of backed my way into a neuromechanics career, I guess.
Great. And Helen?
Yep. All right. So my undergrad is also electrical engineering, focusing on control. Then I became really interested. Actually, initially, I'm really interested in brain-machine interface. That's why I applied, graduate school at ASU as well, from Jiping He's lab as well. Have a 1 year overlap with Doug, and so I would say, once I joined the lab, I get more interested actually in rehabilitation engineering. And my initial work mainly focused on control and signal processing. And that time, a lot of algorithm doesn't call machine learning. So we run a lot of predictions, classifications, estimations. And also in terms of control, we use a more classical control rather than those learning-based control that I'm working on. And then after joining my postdoc at the Todd Kuiken's lab at the Rehab Institute of Chicago, now it's Shirley Ryan, and I started to work on machine learning heavily, working on prediction, decoding the neural signal using machine learning approach. After being independent, I started to drift back for the modeling, and now I'm combining both machine learning and the model together. So that's kind of my take why I'm interested.
Yep. Great. Yeah, I love this theme of sort of controls, right, as being a theme I keep hearing coming up. And even though I am actually now a professor in an electrical engineering department, I have no degrees in it, actually, don't tell them. But and I
don't have a degree in mechanical engineering either, so don't tell anyone.
Yeah, but I think controls for me was really when I realized, sort of when I learned about control theory, was really when I actually almost wished I had been an ECE. For a lot of my training, I think it's a really powerful kind of concept. So it's exciting to see sort of that theme emerging. Great. So my next question is, when I was excited about this topic of human device interactions, but I also find that this can kind of capture a lot of different things and sometimes means different things to different people. And so, thinking, for instance, about the physical interactions between an exoskeleton and a limb, but then there's also things like sensory feedback that devices provide to people, and so on. And so maybe could you each touch on kind of what kinds of interactions you focus on most in your work? So maybe we'll start with Helen for this one.
All right. So I work a lot on this efferent control, the motor control, neural control. So basically decoding the human's neural signal and then trying to understand their intent and then drive external machine, like a prosthetics. That's one of the big track of what I do. And then another area would be this human robot symbiosis that I'm currently working on. Is basically this interaction is in a functional. So how these two intelligent, so assume the robotics device, it has intelligence, there's autonomous control there. So how the human control and the autonomous control can collaborate and coordinate, work together as one. So example will be currently using a reinforcement learning to generate a personalized control mechanism to coordinate with the human for better walking gait.
Great. And Doug?
Sure. So the interactions I focus on primarily are direct interactions with neural pathways, but the sort of understanding of those interactions and how to use that interface is really based primarily on our understanding of what those neural pathways do in controlling physical interactions of limbs and the environment. And specifically, I'm interested in understanding how sensory pathways from the limb shape motor outflow to muscles, even muscles that are weakened by stroke or spinal cord injury, such that we can use those sensory pathways to augment or compensate for some diminished input to motor to those motor neurons because of some stroke or injury. And so a recent paper that just came out yesterday shows stimulation of sensory pathways projecting to motor neuron pools in the cervical spinal cord. By electrically stimulating those pathways, we can boost activity, voluntary activity of muscles that are weakened by stroke. And so, again, it's these sensory pathways that really enable us to interact deftly with objects in our environment, whether it's walking or reaching and grasping. It's those sensory pathways that are really crucial for enabling that control. And in cases where that control is disrupted, we can use those same pathways to try to provide some assistance.
Great. Yeah, and congratulations on that paper. I saw it scroll by my newsfeed, and I'm really excited to take a closer look. It looks very exciting.
Thanks. Oh, thanks, Teresa.
Great. Let's see. And so a kind of follow-up question on there. That this, I guess speculating a little bit, maybe thinking outside, more broadly about the field, do you feel like there are kinds of interactions, right, that happen beyond sort of this sensory motor interaction, and then some of the, sort of interactions that Helen was commenting on that we need to be thinking more about as a community? Are there, I think there's Helen, I think we share a real interest in sort of this question of how intelligent agents and robots can interact with, intelligent agents that adapt in people. But I'm curious if you guys can sort of comment on, what you see as kind of open challenges or kind of directions that we're maybe not yet thinking about or need to think about a little bit more.
I could maybe start with a little speculation. I mean, so I think there are clearly sensory motor integration problems that relate to using sensory feedback to shape motor output during ongoing physical interactions. But then there are likely also more exploratory or kind of system identification functions that are supported by those interactions as well. So, our brain's ability to develop an internal model of the world and the objects in it must be shaped by the physical and the experiences that we have when we interact with the environment. So, as we move, we gather sensory experience, and how that sensory experience shapes our internal models of the world is something that I would like to learn more about.
Yeah, that's a really fascinating question. Definitely something that we talk a lot about in the lab, and I think is challenging to get a handle on. I think that term internal models sort of comes up a lot, but what is it, right? And can we start to operationalize it as engineers even, right, to then think about how to use it for rehabilitation?
Clearly, it's a set of MATLAB scripts that are hardwired in our brain somewhere.
Right. Yeah.
Yeah, I want to follow up this as well. So recently I had a conversation with Lee Fisher actually, and then Rob Gaunt on this like a sensory motor integration, because a lot of for example, the bidirectional neural interface. So people give a sensory feedback they usually study the sensory feedback without consider the motor side of the, the motor control side. Usually they address one side at a time, but essentially this has to integrate, like, are the resolution the same? Is the reaction time the same? How that influence, right? So can this enhance the internal model generation work with the brain control? I just saw that this part is lacking. I definitely want to see more research on that side. The other one, Amy, we shared the same interest, working with the human brain, has a robot that has to be intelligent. How these two are really coordinated with each other, to me, is it's such a hard question, right? How did you modeling the humans, the goal, right? How do you know the human goal, their intention? So I saw that this area, I do see your group is evolving and continue generating an interesting paper. We also working on this in the sense of locomotion context.
Right. Yeah, I think these are two really great kind of themes of questions, and this one of the fascinating and frustrating challenges of all of these systems is that they're all ultimately closed loop, right? So the sensory motor, the robot human, it sort of becomes very difficult because you can't operationalize any individual piece, right? Because ultimately the interaction is kind of at the core, right, of the problem, but also the opportunities there. Great. All right, so I want to kind of shift gears a little bit towards thinking about kind of the kinds of the flavors of how we approach problems, I guess, in human-machine interaction. And so especially when a theme that kind of has come up in this workshop is sort of the questions about when we want to think about personalizing devices, right, to individual people versus sort of convergence and coming up with therapies and approaches that tend to work well for individuals. And so I'm curious if you guys could comment on, particularly in this framework of thinking about the interactions, right, between within a device, sort of where you see these two different ends of the spectrum playing together.
Helen, do you want to start with that one? I think that this aligns squarely with many of the things you are working on
Okay.
right now.
Well, I think the personalization in the context of rehabilitation, I just saw that need everywhere. Having as a person that I work with multiple patients population, it is always true that everybody is different. I never had running one idea and then test on every patient, it work out for everybody. So personalization, I think it's a key. And now we have this capability to generate the personalization, a different personalization approach, either using modeling or maybe a model-free approach. But we see more and more related to that. So I definitely feel like if you ask me like where should it be used, I would say for neuro rehab, it should be everywhere. So what's the second question?
I think that was the main one. I think just, do you see the role of personalization as particularly important in the context, I guess, of like human device interactions?
Absolutely. So that's what I do. Yes.
Right. Yeah. Great. Yeah,
and I agree completely. Without question, where we can, we should try to personalize all treatments. Whether it's a rehabilitation treatment or a cancer treatment. Clearly there's been a long-standing effort to try to make medicine as a whole more personalized. In the context of rehab, that is also clearly true. To do so, to really scale that solution is a challenge, but I think it's predominantly an engineering challenge that I think our community is maybe uniquely positioned to address. It's going to require, instrumentation and math, to really solve it. But again, I think that's what this community that's assembled here is really interested in working on.
Yeah, I do agree. I felt like for the traditional, like let's say the device, we're talking about human device interaction. If the device is like a brace or, like old fashioned brace or prosthesis, they own or socket, let's say, that this physical interface has to be personalized. That will be the job of a certified prosthetist and orthotist to work. But now, when the device has more intelligence, this interaction, I think, from the physical contact all the way to function, that the personalization is the key.
Right. Yeah, so Doug, you sort of touched on kind of challenges that do come up, technical challenges that come up with personalization. And I'm curious, as someone who's familiar with kind of the commercial translational aspects of, taking these devices and trying to turn them into products, can you comment on kind of how this goal of personalization maybe interacts with the realities of companies, and then also thinking about like regulatory agencies? And are there things that we as engineers with this goal of personalization kind of need to be thinking about to make sure that those therapies ultimately are translatable?
Yeah, absolutely. I mean, I'd be curious to hear what Jerry has to say about this as well, because he has way more experience on commercialization than I do. But maybe to start, for a therapy to be practical, it needs to be something that, a large community of practitioners can implement, right? And the training and expertise of, those practitioners is going to be varied across the community. And so the systems that we build, I don't want to say need to be foolproof or dummy proof, but they need to be relatively easy to use, right? Our graduate students and our postdocs and ourselves, we're not going to be going out into the field to support those devices. And the more sophisticated those devices become, the more difficult that scalability problem is, right? Deep brain stimulators, for many years only had a few channels. Now with directional leads, there are many more stimulation patterns that can be implemented on the lead. And the programming problem for those devices is now much more difficult than it was, even though the number of contacts really isn't that many in comparison to the things we use in our research labs. And so medical device companies like Medtronic and Abbott and others are grappling with this problem right now. How can they automate or maybe leverage AI-based methods for streamlining that programming process, because that is the therapy, right? And the choice of stimulation parameters that you use, is a critical determinant of whether or not the therapy works. And if you have to spend hours turning knobs to find the right dose or the right pattern, it's just not feasible. It's just not practical. And so again, I think we need to know which signals to measure. We need to know what to do with those signals, and then we need to know how to turn that sort of feedback into a prescriptive plan for programming the devices. And again, this is all based on modeling, right? Right.
Yeah, I think that point about sort of needing to be able to carefully operationalize, right, and restrain the space, right, within the context of personalization, and finding, those most effective, right, dials to personalize that are relatively simple but still offer the most kind of personalization.
And what's effective at one moment in time may be less effective or ineffective at another moment in time, right? And so being able to anticipate and compensate for changes in the system we're trying to help is critical. And again, having sensors or some some sort of monitoring system for knowing when and how to make changes, I think, is critical.
Yeah, great. And so Doug, you mentioned sort of AI and machine learning. And so let's now talk a little bit about some of the kind of computational tools, right, we might need for getting some of those personalization goals in human computer interaction. So machine learning obviously has generated a lot of excitement where we can potentially just kind of learn relationships from the data itself rather than having sort of detailed models. But obviously in neuromechanical systems, we have a lot of musculoskeletal models that give us kind of important insights about the underlying neural circuitry and the biomechanics. And so where do you see kind of the roles of these two different kind of computational tools? And we'll start with Helen, because she has a very interesting paper kind of on this topic that sparked this question.
Okay, well, since you cued me, so I will use my example, my research, which is decoding EMG signal for persistence control. So at the beginning, what I learned is from Tuck Haken and Kevin Engelhardt at the University of New Brunswick. Is all about machine learning, pattern recognition. So you put a bunch of electrodes, you don't really care about the physiology, and then just say, hey, can you tell the pattern difference? It worked really well. The problem is, as a lot of people working on machine learning, the learning transfer, right? So when the condition change, then sometimes it doesn't work. So what are you gonna do? And then I had a really interesting conversation later with actually Andy Schwartz at the University of Pittsburgh now. And then he asked me, he said, well, you know the physiology, right? But why don't you use that information? That made me click. I was like, exactly. So actually, after that, I started to say, hey, actually, I can use the model, the musculoskeletal model, to do this. So I work with my colleague, Kay Saw, and then also my postdoc, Dustin Crouch. So he is currently at the University of Tennessee. So, and then they started to work with me and started to introduce this musculoskeletal model. And I learned a bunch. It works. It works. But you have to specifically identify those muscle for amputee so hard. And all those parameters, gosh, it's a lot of parameters that you have to optimize. So, and then after that, I realized both has a pros and the cons, but the modeling approach is definitely can extend. If your training data has no such thing, but the model is still existed, then it's still gonna work. So later, currently I'm working on combine this both together, right? So for the things that you just had a hard time to estimate or generate a model, so maybe you can just use a neural network. But for the things that you definitely know, you could using a kind of like a dynamic model. So adding them together is actually really powerful. So one of the paper probably you saw recently is that kind of a gray box approach.
Yeah. Great.
Yeah, I completely agree. I think that we shouldn't ignore those things we know and understand and especially can model, right? If we know the physics and we can model the biomechanics, let's not ignore that information. And yeah, I know some other people feel differently about this, but I certainly feel strongly that we shouldn't ignore those things. We should leverage them, especially for medical devices where being able to understand and predict the behavior of systems, especially complex systems, is critical, right? And so the more knowledge we bake into those devices, I think the better our understanding of their function will be.
Yeah, that's a really great point of thinking towards, making safety guarantees and things like that in any of these kinds of, human device interaction systems. Yeah, I think these kinds of more principled modeling approaches, right, will be very valuable for that kind of a goal. I'm curious, Helen, kind of in this sort of journey you're on to try to marry these two, are there challenges in this space? Kind of what are key issues that you see? Okay,
well, so spoiler is I currently work with a Kate. Because I use the reinforcement learning, and then we are trying to use reinforcement learning to optimize the musculoskeletal model. So hopefully she will, in a keynote, she will talk a little bit about it. So my student is still trying that. I think whether or not this can be scaled up, I think, the scaling, because the model is just so, because she work on upper limb, there's so many muscles. And I told her, I said, can we just do one thing at a time, maybe one or two joints, rather than addressing all the hands, fingers. So I think that part we are still thinking like what is the best way to approach that. Yeah, so that, and then also for a lot of lower limb, because walking is a cyclic, so then you know exactly what task you're going to collect and be able to run this optimization. But for upper limb, it's just so variety of possibility using your hand. So that's another thing. You know, what is the specific task or context we could use for training this, you know, personalized musculoskeletal model? I thought that that's also a very interesting question for the community to work on.
Great. Yeah, I think this importance of kind of potentially constraining machine learning algorithms, right, based on principles we know, I think is definitely something that has come up in my corner of the world of brain-computer interfaces, where, you know, people will develop algorithms that offline are much more predictive from neural activity, but they don't necessarily help very much when you actually use them in kind of a real brain-computer interface. And there's actually a really lovely paper from Steve Chase's group over at CMU that kind of points out the ones that work best are ones that are basically physical control systems that have kind of real interpretable physics. And so I think there's some real insight there towards, you know, this idea that, you know, we have to constrain the models in some kind of reasonable ways.
Can I maybe just add a quick follow-on point? You know, so oftentimes our ability to implement like deep learning approaches, which are very data hungry, is often limited by the size of the data sets that we can actually generate, right? And so to the extent that we can use models of the parts of the system we understand to generate larger data sets that can maybe then support training of the AI-based elements in the system, I think is also a valuable use of modeling.
Yeah, that's a really great point. Always I'm fascinated by the excitement about deep learning techniques and neural interfaces, because I can think of few applications that are more data limited, right?
Right, exactly, exactly.
Yeah. Great, let me see. So I think my other sort of main kind of technical question was thinking about, again, this idea of machine learning and ways to sort of, it opens up opportunities, right, to start having sort of smart devices or intelligent devices that adapt in kind of smart ways. So you both touched on this, you know, point that you kind of have to take into account that, you know, the person is potentially evolving and over time. And so what do you both see as kind of the biggest opportunities and potential challenges of kind of using that sort of smart adaptive AI in the context of rehabilitation applications? Either I'll throw, I'll let you guys decide who wants to start.
I mean, I'll give my simple answer because Helen knows much more about machine learning and AI than I do. You know, but I think that the sensorization that is needed to sort of track the system is really critical to the you know, to ensure that whatever the system you're using is adaptable. And so developing simple ways to measure the state feedback, you know, whatever that state feedback is, to know when and how to adapt the system control is probably critical. You know, and it's not only going to be based on the output of the system, you know, the output of your ML system, but the person's state as well. So whether it's, you know, EMG based or IMU based or some combination of biomechanical sensors, I think some sort of sensing modalities are going to be important for tracking that.
Yeah, I would probably share what my research facing in terms of using a reinforcement learning that, right, so reinforcement learning will toning prosthetic device. So that's what I do. And then to personalize this device control that fitting the person's better to generate a desired gait pattern, for example. So after, you know, things are learned, there's a policy. The policy actually can be used as an adaptive machine, right? So, which is great. However, the human device goal for walking, locomotion might change. For example, amputee, at the beginning, maybe their emphasis is more on the stability. But after they use it for a while, they adapt to it. Then things became metabolic cost reduction. How do you know that, right? So this adaptation is beyond just, well, you have a policy and that's it. But the goal is also drifting. Like, how did you capture that? I just saw that this is such a hard question. Again, right, if we have a better, more things that we can measure, for example, potentially we can learn this. But still, I haven't seen longitudinal personalization that I saw in the field.
Yeah, I think that's a really great point of sort of that. Yeah, you have to understand what things to adapt to. And then kind of to Doug's point, you have to have the right sensors to be able to measure, right, that thing is changing over time. And that can be potentially a really complex space, right? When you think about sort of a full system and rehabilitation that may span kind of really long timescales. I think, Helen, your example of someone's goal changing over, long periods of training is a really interesting one. Yeah. Great. And so maybe, on that note, we can sort of switch to thinking about kind of what you see as some of the biggest kind of gaps in our knowledge when we think about building these kinds of, devices that are personalized and can adapt to people over time. What are the pieces that we don't have yet that we kind of really need most to start getting towards that goal? Any thoughts? And in particular, I'll maybe ask to, I think there's two things, right? Well, in many cases, it's, what scientifically don't we know, but then also kind of from a modeling perspective, are there kind of computational tools that we maybe don't have yet?
I will start with a little thing first. So I know in the field that people always are calling for a big data. And I think, if you look at the neuro rehab literature, many study has case studies as a very limited data available. I wonder, whether always calling a big data approach, can we generate a more approach that is data efficient? That would allow, given a certain amount of data from individual or maybe maybe 10 people, can we learn something useful, grasp some information useful that can extend beyond us? So that's my, I would say, I always think, people always say the big data, like where the data, and then everybody collect the data in a different way. I wanna see if anyone has a thoughts on this one.
Yeah, I really like that term, data efficient. Yeah, because especially when you think about real applications of these technologies, that seems so crucial. Yeah, Doug?
I guess the example that comes to mind from my world is really kind of a limited understanding of the neural circuitry that we're trying to directly modulate, right? So in the context of spinal cord stimulation or DRG stimulation, we can predict with reasonable accuracy which fibers are going to respond, when we deliver electrical stimulation, but the consequences of the activity that is generated by that stimulation are somewhat predictable, but not completely predictable, right? We see in the patient work that the effects of stimulation varies with the activity level of the patients that we're working with. So if they're actively engaged in a task, we see changes in muscle activity. If they're resting, we see no effects of stimulation on muscle activity. And so, a better model or a more complete model of what effects stimulation is having on the motor system will certainly help us design stimulation patterns and programming methods that work most effectively for helping those people move. And I don't know how run more experience.
I'm curious, kind of thinking about both of your responses, kind of where you see our ability to incorporate also the time history or sort of the time dependence of these systems. Where do you see, because to me, at least, you know, as someone who thinks a lot about kind of learning and plasticity, I don't know if could you guys comment? I'm trying to formulate a question on the fly, but how well are we capturing those kinds of effects in these systems right now?
I saw that's the theme for the session 1,
right.
modeling the plasticity,
right.
Which is really hard.
Yeah, in my case, we're not doing a very good job yet, but it's certainly one of the focuses of our work. Right, our immediate focus is on understanding the direct, immediate effects of stimulation on muscle recruitment. But we're surprised initially to see changes occur over the span of a month. And now we're at the point where we're seeing changes on a trial by trial basis where we're seeing the patients adapt in real time to the changes in their musculoskeletal function, right? Because we're producing a change in their neural circuitry, which has a direct effect on their ability to move the arm. And of course, that changes how they have to think, go about controlling the arm. And so, we're just at the very early stages of measuring and trying to understand those processes.
Yeah, I definitely see the adaptations very important. Training the user to use these robotic prosthesis or exoskeleton is important, but less emphasized in the field. And then including, it doesn't matter what type of control it is, neural control or autonomous control. Human really has to adapt to it because essentially you attach something which is a machine, no longer a biological system within the body. But in terms of modeling that, again, I circle back to the session 1. If there are a really good model, I thought that this will be a tremendous for a model that can be used, and then the parameters can be measured and plug in. So those are the parts I think that will tremendously change the field.
Great. I think we've got a few more minutes before we'll open it up for Q&A. So sort of as the last question, we'll gear this more towards trainees that might be in the audience. So for people that have found this kind of work that we're talking about interesting, what sort of recommendations would you have for someone who's interested in kind of getting into this research area?
Yeah, good question.
Okay.
Certainly read the literature, study the neuroscience as much as the biomechanics, because I think the neurophysiology that underlies these systems is absolutely crucial. Certainly we can learn a lot from studying only the biomechanics, but especially for questions related to adaptation and plasticity, understanding how those processes work at the level of the neural circuitry, I think is critical. It's not the only part of the problem, but it's a critical part of the problem.
Yeah, so I actually listed this as one of the current gap, is that I felt people working on, maybe biomechanics, they are started to get into the field of using machine learning, that I definitely see the trends there. However, when I sometimes interact with some of my colleagues, and then because, this machine learning approach is available too, and then that's, that you could simply apply. But I felt like the student, the next generation, needed to dive into a more detail, like how this works, what is the appropriate way, right? So how did you really implement that? Understand the mathematics behind it. To me, is also very, very important. Otherwise, it's just adopt a tool, but how do you know the tool is applied correctly? I think this is also applied to machine learning folks to come to, the neuroscience or biomechanics. What things already know, right? So if the things already know, why you use machine learning to do that? And also, is your estimation or prediction, is it make sense physiologically or physics? Is it make sense? So I think that will be, so the training, if you work on this kind of interactions of data-driven or physiology driven approach, I would say having a good grasp of both is very important. That will go far for the career.
Yeah, I think that, point about kind of the underlying principles, right, is sort of can be so important, and especially when the ultimate goal is application, it's sort of tempting to try to get distracted by the tools and the specific application, but it's enabled so much more, right, by the underlying principles and understanding. So great. All right, so I think with that, I will now maybe sort of open it up to members of our audience. If you have a question for our panelists, sort of based on any of this discussion, please feel free to chime in, and you can raise your hand.
Well, I'll always have a question, so I'll raise my hand virtually. So thank you guys. It's always so exciting to see. Thinking about the clinical translation piece, how do you see, especially with some of the neuroethics pieces, explaining these technologies and where we understand and where we don't understand how they work, both to the patients as well as to the clinicians? And at what phases in your research do you think about those processes?
Good question. I don't know, Helen, do you want to start, or I can? I mean, you do a lot of patient work.
So that didn't understand is that, are you talking about like how you can explain what like a kind of a machine learning approach generated? Is it right?
A little bit about, well, so it's especially with this like co-adaptive, and especially with some of the stimulation and brain computer interfaces. The truth is often like we're seeing good outcomes, but we're not exactly sure why we're seeing good outcomes. And then there's just a lot of neuroethics around, interfaces with the human body that are co-adapting and influencing this plasticity. And so it brings up, I think, a lot of really interesting neuroethics alongside the computational modeling. And so, but figuring out when and how to explain those and to what level of depth is an area I know, at least I struggle a lot with these new devices and techniques. Not sure if that helps, but that's where my confusion is coming from. And I'd love any thoughts you have on it.
I mean, I think it starts with transparency, right? You try to explain to all stakeholders as clearly as we understand how these, what is the intended purpose of the technology, what we know about how it works and what its implications on their life and their health and welfare may be. If there are safety risks, those need to be identified clearly and understandably upfront. And yeah, I mean, at the end of the day, I think the patients and caregivers, may need to, will ultimately need to make decisions whether they consent to be part of a study or choose to use some new device, and they need to be equipped with, all of the information that we have available to guide that decision. And oftentimes the least certain part of that conversation might be the benefit. We can probably clearly articulate all of the potential risks, but in the case of new therapies, the benefits may not be well understood. But at the end of the day, it's a cost or a risk benefit decision that the patients have to make.
Yeah, and I'll just make a quick connection back to kind of some of the topics that we were discussing earlier about this may be where kind of, Helen's gray box approach, right, of machine learning algorithms that are informed, right, by principled models could actually potentially be really helpful for this particular goal, right, that you raised, which I think is a really important one of, how you talk about these things, right, with the ultimate
both on the explainability and perhaps on the forecasting of outcomes, right? Because you may be able to make a more accurate prediction of how someone may respond to your treatment if you can actually model the system that you're trying to support.
Yeah.
It can also be a great spot for modeling and tying it back to the physics-based models and the physiological-based ones. That's a great loop. Sorry, Helen.
Oh, that's what I'm actually want to say is it's actually, well, that I would let Kate to talk about this when she's a keynote speaker for this session.
Great. Are there other folks that have questions?
I'll just point everyone to the chat. Oh, go ahead.
Hi, this is James, in case you can't see me. So I think one of the, as an engineer in a PT department, I think one of the interesting challenges that I've observed is the challenge in bridging, whether it's physical technology and devices or computational techniques, and getting buy-in from the clinician. So in thinking about the challenges with translation, of course, there are a whole sort of set of regulatory issues, but you also need to convince clinicians, let's say physical therapists, who may not be trained to use devices in the context of their practice. So can you all maybe speak to thoughts you have about how we could address that challenge, or if you have addressed it head on in your work or experience in any way?
So I've worked with a number of clinicians over the years, and I think, mind you, these are in academic medical center settings, but in general, if they are convinced that there is a potential benefit for their patients, they would be willing to at least try it. Obviously, there are practical limits to what they can do, but if they really think, if you can convince them that you may have some better way to help their patients, they would usually be willing to give it a go. But yeah, obviously there are constraints.
So James, I just want to make sure I understand clearly. So you're asking how we can convince the clinician to buy in and then use the new technology? Is it
Exactly, yes.
Okay. Yeah. Well, my situation is I have a bunch of very collaborative clinicians who are always actually looking for novel technology. So the clinician actually come to me and say, "Can I use your hip axle for doing these things?" Which is super interesting, Rather, I mean, they are definitely not using it for treating patients, but they are actually very curious about what this device can do to their patients, seeing the potential. So I guess I'm just lucky has a UNC School of Medicine faculties here to support my research.
Yeah, I think those are both really interesting answers, and I always wonder how much it is the environment and the clinicians who happen to be affiliated with our institution versus how that might change when we try to interact with a broader community who may not be in these types of institutions. Thank you.
Yeah, this is slightly off topic, but because I'm far less clinical than either of our panelists, but I find I'm often in the situation of trying to convince engineers to do the slightly simpler thing. And in many cases towards a goal of sort of making it potentially more biologically rooted or, based on sort of principles of how neural circuits work. And so I think there's interesting push-pull right there, where we need ultimately buy-in from all of the potential stakeholders. Yeah.
Engineers love feature creep.
Yes. Yeah. Great. All right. I think we're to be respectful of everyone's time. I think we'll wrap it up there, but I want to really thank Doug and Helen for a wonderful discussion. And then I'll pass it off to Kat. I don't know, did you have something you wanted to add quickly?
Oh, no, yeah, I just want to say, please join us all in giving a hand for Amy, Doug, and Helen for joining us today. We really appreciate it. In 10 days, it'll be our conference, both virtual and in person at the University of Southern California. So we're really excited about that. We'll be sending out the links to this and the prior YouTube recordings. And then also don't forget to introduce yourself on the Slack channel and share any other thoughts and resources over there. Thank you all again, and we hope you all have a great rest of your afternoon and evening or night. I saw there were some international folks as well. So thank you all so much for joining.
Forward to seeing you in 10 days.
Yeah, thank you for including me.
Yeah, thank you.
Thank you, Kat. Hey, Doug.
Hey, good to
Just
see you
want to
guys.
say hello.